Hello, dear friends. I would like again to point your attention to the invisible so that we can explain the visible and we can study the miracles and the wonders of the nature, and specifically in the substance of water, which is all around us. This lecture is going to be a little bit more difficult, but that should not discourage you to study it. Maybe you should revise it 2-3 times. We're going to talk about how the atoms get bonded now with each other, because there is a different kind of bonding. Like in the human relationship, you've got different kind of relationship. So with the atoms, you've got different kind of relationship between atoms, and we're going to study in this lecture exactly that, how the atoms get bonded, and also to the molecules also. But I'd like first to tell you that there is generally 4 types of bonding. And we're going to start first with the most basic one. It's called ionic bonding. We know already what is ion. That means an atom which gained or lost an electron. When the atom gains electron, becomes anion or negative ion. And when the atom loses electron, because when it's a neutral, when it loses electron, he becomes positive, because the protons now are more than the electrons. So now it becomes cation. So now what is happening is when these 2 charged particles, one is positive, another one is negative, they attract each other with the second biggest force in the universe, as I said to you, electromagnetic force. They attract each other and they unite, but they don't share electrons. You remember last time I told you that chemistry is about sharing electrons, and we have chemistry only when we have electrons. If we don't have electrons, we don't have chemistry. Now, the electrons here, they are not shared in a way of cloud, but what's happening, the strongest atom pulls electron from the weakest atom, if we can say that, and actually steals the electron, and this is why I've got one more and the other one has one less. This is, it's called ionic bonding, and the ionic bonding we can see with the sodium chloride, a basic table salt. The sodium loses electron and the chlorine gains electron, and now the chlorine gets negative and sodium gets positive, and they unite, and this bond is very, very strong. This is why ionic compounds got very high melting temperature. In the case of salt, 800 degrees, you need a lot of energy until you start melting the salt. That's the first type of bonding. The second one is when actually the electrons, like I explained to you last time, they actually share their electron clouds. Now the molecule has one big electron cloud around it. We're talking about only the valence electrons, not every electron, only the valence, the one that are at the shell. And out of that, only these that are conductive of making an octet, 8 electrons in the shell. So now what's happening is when the electric clouds get shared, now we've got a valence bonding. And this bonding, valence bonding theory, was invented by Hitler, the one who started first, and that he says that the physics eats chemistry with a spoon. This is, if you remember, Hitler, in our first lecture. So that's the valence electron. But now some of them, of the combinations, one of the atom more strongly pulls the other atom to each other. So say for example water that we're studying, the oxygen pulls the electrons more from the hydrogen, and this is what's called polar covalent bond. Now, oxygen is not so strong like a chlorine to pull completely the electron from the atom. Sorry, the oxygen is not so strong as the chlorine to pull the electron from the hydrogen. This is why it's polar molecule, but it is covalent polar. And then after we've got this was the third one. So the first one is ionic, second one is covalent, the third one is polar covalent, and the fourth one is metallic bonding. This is one of the strongest bondings. What's happening now? The valence shell of the metals, all metals, get the electrons in the valence shell, they get shared. Now, what's happening is it becomes like a sea of electrons around this metal nucleuses. And this is why all of these electrons now push so strongly, get attracted to the nucleuses which are in a lattice, metal lattice. It is very strong. This is why metals has very high temperature of melting. You know, some of them are like in the thousands of degrees, like titanium. You know, some of them are the biggest, especially have a very low temperature, like tin and lead. Now, if you remember something, why gold is yellow and why mercury is liquid? They've got such a massive nucleuses that when the nucleus became so massive, the valence shell electrons gets closer to the nucleus, and because of this closeness they are not available for metallic bonding, and this is why mercury is liquid and gold is soft. Actually, before they used to test it when the coins or a piece of metal gold were pure gold at the medieval ages or before, even in the antiquity. They used to test it by biting it and see if there is a nick on the coin or on the piece of metal. And if there was a nick, that means it's genuine. Otherwise, the other metals doesn't have such a big electron cloud, so the effect, the relativistic effect that we talked last time, is not so strong. But remember why it's yellow. It's yellow because when there is a relativistic speed of the electrons with the valence shell, what's happening is the length is reduced, and when the length is reduced, the lights get shifted, the absorbed lights get shifted to the blue, and this is why we see it as a complementary color, yellow. When the one piece of the spectrum is absorbed in the piece of any piece, any substance, we see the complementary color. This is why if you see the red color, that means the green is absorbed. If you see blue color, that means yellow is absorbed. And when you see yellow color, that means the blue is absorbed. So it's not only weakening the bond and getting soft, but also it starts absorbing certain colors. Now with the mercury, that's to the extreme. The mercury gets such effect, relativistic effect of increasing the mass of the electrons, because relativistic speed, portional speed of light, that they get closer to the nucleus, and they are not available now so many. There are some few. This is why we've got mercury conducting electricity, and this is why it's shining, but they are not available so many for bonding. And this is why mercury is liquid. It's not like the iron, solid, and it's not such a high temperature with melting. So this is the reason why we've got this, if you remember, with the metallic bonding. Metallic bonding is one of the strongest bonds. Now if you see, say for example, iron atoms, see they get together in a special metal lattice, which all of atoms share electrons, and all of these electrons are moving around. This is why metals are excellent conductors of electricity. because the electrons are actually free to move wherever they want. But because of that, the bond is extremely strong, because all the electrons that swim around are holding the nuclei together, and this is why atoms are bonded very, very strongly. And this is why, because of these strong bonds, they got very high melting point, the metals. Now, there was a brilliant scientist, Linus Pauling, 2 times Nobel Prize winner, and he lived a nice long life, and he started actually studying chemistry since he was a young boy. And he discovered something very well, that the atoms get bonded and the molecules get different kinds of bonding between the atoms because of the property which you heard about in the video. It's called electronegativity. What is this electronegativity? In plain language, electronegativity is when one of the atom strongly pulls electrons, the valence electrons in their bonding, more towards itself. Just like the polar bonding of water, the oxygen pulls more electrons to itself, simply because it's more electron negative. This is why it pulls the electrons to itself. So he created a very nice a table, and he started showing the elements in their electronegativity. So now you can see, this is the table that's available to us. So now, as you can see, now you've got different electronegativity. The electronegativity varies from the least electronegative element, francium, or cesium, say, for the one, because francium is not very easily available at nature. And you've got fluorine, the most electronegative. And you've got to see huge difference between them. And you can see some of the elements like a fluorine, oxygen, nitrogen, chlorine, they are very, very electronegative. While the other, like alkali metals, they are very, very with very low electronegativity. You can think about, like in the video was shown, it's one is stronger, the other one is weaker. So the stronger pulls the weaker to himself. That's basically electronegativity. And as you can see also, the highest electronegativity is 4, and the least is 0.7. Now, and there we've got a very nice system to see if the bond is ionic, or is it a covalent bonding, or is it a polar covalent bonding. Then we can see that system, we can qualify it very well. If the difference between the two elements is less than 0.4, say for example between carbon and phosphorus, the difference between them is 0.4, then their bond is covalent. Now, if you've got between 0.5 and 2 difference, now say for example oxygen is 3.5 and hydrogen is 2.1. Now this bonding has a difference of 1.4. It's above 5 and under 2. Above 5, including 5, and 2, this is polar covalent bonding. Polar covalent bonding. This is what it is. Also, ammonia, say for example nitrogen and hydrogen, 3 minus 2.1 is 0.9. It's again polar covalent bonding. If the difference between their electronegativity is more than 2, including 2, then it's ionic bonding, like a table salt. Sodium chloride. There is a sodium and there is a chloride. So the difference is 2.1 more than 2, including 2. So this is ionic bonding. See, this is ionic bonding. So in this way, we can see which bond is what by checking the electronegativity. And this is why it's actually brilliant way of showing this point. Now let me explain you again with a nice simulation. Now you've got two hydrogen bonding. The electronegativity is 2.1. You can see that means they're equal. That means the bond is gonna be covalent bond. They're sharing their electrons. See, this is the electrons. Electrostatic potential is there, the positive is there, the negative is there. So now you can see the electron densities all around the molecule. And this sharing of electrons is called covalent bond, because the electronegativity is the same. Now let's study now the water that we study. Now this is what's happening. Polar molecule. On this part the molecule is negative, on this part the molecule is positive. So what's happening, look at it now, if you see the dipoles. So let's move the electrostatic potential just to see it. There is a positive goes to the negative, and there is a positive goes to the negative, and this is why we've got all of these two forces, and because of that we've got the dipole pointing to that direction, and this is why the electrostatic potential is there. More the negative part is there and the positive part is there. It's very polar molecule. Now you've got 3.5 and the hydrogen is 2.1, so the difference is 1.4. So this is why we've got negativity is like a dipole. It's like a little magnet now, or like a battery with a positive here, the blue, and the negative here terminals. So now you can imagine what's going to happen if you meet another molecule like this. The positive is going to get attractive to the negative. Now I'm giving you a clue why the water is liquid, right? And why the say for example, and the oxygen, say for example, is a gas. There is no polar molecule. I say there is no polar. All of them the same. There is no electrostatic potential. There is nothing. There is no partial charges. There is nothing. See, there is nothing. They are equal. Look at it. Well, the water, you see, you've got more charges to that way, stronger. See, stronger. This is why we've got all of this polar molecule. Now, this is the molecule of water, as you can see, and you can see it's polar. You can see it clearly. That's the case. Now, look at this molecule. Now, this is the molecule of water. Now you can see the shape actually of the molecule. All right. So what's happening is we've got these two hydrogen atoms bonded with polar covalent bond to the oxygen. But now the oxygen got how many valence electrons? 6. With 2 he participate with this connection, so 4 left. And this is the electron clouds of the lonely pairs that are not bonded. You see what's happening now. And because of that, the molecule is bent, because these electric clouds are actually pushing these bonds downwards. Look at it. if it wasn't for these electric clouds, the molecule would have been like a carbon dioxide. There is no free electrons to push the molecule down, and although the molecule is polar, it's not such a point like the water. We got free electron pairs which push the molecule this way. So now we've got all of this angle like here. Now we've got angle, and this angle, it's almost 105 degrees, and the structure is like a little pyramid. Look at it. It's called tetrahedral structure, and it's bent. While you can see the carbon dioxide is not bent, it's 180 degrees, and this is why carbon dioxide is a gas, but water is liquid at normal temperature. Look at it, whatever. So we've got here another thing that we need to be aware of: steric number. What is steric number? It comes from the word stereo. Stereo. And stereo in Greek, stereos means three-dimensional or solid. So now we've got the three-dimensional structure of the molecule. Okay. We found out, like in this case, how the bonds are done and how the polarity is done due to the electronegativity. Alright, we found it. And we found that how the molecule is polar or non-polar, and how the molecule is actually bent or not bent. Alright, so now we can see here that the three-dimensional model of this molecule of the water. How we show it's like this. This is done not by the valence theory. This is done by the valence shell electron pairs repulsion theory. So we've got pairs of electrons here, pairs of electrons, and pairs of electrons here. The electrons, as I said on the first lecture, they try to stay as far as possible from each other, and this is why we've got this tetrahedral, like a pyramid structure. And because we've got these two electron clouds of the lonely pairs, they push all of this molecule down. Nothing pushes this molecule down, the carbon dioxide, because there is no free electrons, no lonely pairs. You see, no lonely pairs. Here we've got two lonely pairs, and because of that, another reason the water to get very not only electronegative, but now you've got a shape of a molecule which is conductive of the molecules getting closer to each other. So when they're closer, the water is liquid. They're not like the molecules, they cannot be so close in the carbon dioxide at room temperature. This is why we've got carbon dioxide is a gas. Let's go up to the valence shell electron pairs repulsion theory. So now, because of this, they repulse each other. Now this is why they take this shape, and because of this angle here, the water is liquid, as I said to you. So the valence shell electron pairs repulsion will tell us the structure of the molecule. Some of them are very complex, and the valence shell electron pairs repulsion theory, actually it's responding to that very well. The steric number is the number which the oxygen in this case is bound or have the electron, the lone pair electric clouds. So now we've got the steric number 4, because you've got these two, and you've got two lone pairs, so it's actually 4 steric number with the stereo. I said to you, the Greek word stereos means three-dimensional or solid. Now this theory shows us what is going to be the molecule. Now if you look at the ozone, the ozone steric number is 3, not 4, because you've got 2 bonding electrons here, 2 bonds, and 1 electron cloud here. You see? So this is why the steric number is dynamic. It's not static. It's not always the same. I just wanted you to realize that. So this is how it's done with the oxygen. With the water, we said it's different, right? We've got 2 lonely pairs, so the steric number is 4, just like here. Now let's look one more time on this connection. Now I've got 2 molecules, and both of them are covalent, so there is no polarity on the molecules. But when they get together, what's happening? One of the molecule electron clouds get attracted to the another molecule. What is happening is when the 2 molecules which are covalently bonding, atoms that are covalently bonded and they are not polar molecules, when they get together, see, you see there is no attraction between them because they are not covalent bonded, and there is no the molecule is not a polar molecule. But now when they come close to each other, see what's happening when they get closer. The electron clouds of one of the molecule gets more positive and the other one gets more negative because get attracted by the positive nucleus. So they became very temporarily, they became also attracted to these 2 molecules, and these forces is called London dispersion forces, because these electrons get dispersed, and this is why it's called London dispersion forces. See, this is how this molecule became temporarily like dipole, like the polar molecule. Then we've got another bond, another type of bond, the polar covalent bond between these 2 atoms, and this polar covalent bond creates a polar molecule. You've got a dipole, and dipole is attracted to another dipole, the positive to the negative, and this is why we've got this bonding. Now it's called dipole bonding. You see, dipole bonding. Now we've got the strongest dipole bonding is hydrogen bonding, right? And then the hydrogen bonding is between the hydrogen, which is connected to only 3 elements: oxygen, nitrogen, and fluorine. When the hydrogen is connected to these 3 elements, now it's get connected to the other atom, and this is called hydrogen bonding, and this is the strongest dipole bonding. It's called hydrogen bonding. Because of this hydrogen bonding, look at it now. The water has 2 atoms of hydrogen, and we've got 1 atom of oxygen. Now this molecule can make 2 bondings, because first you've got 2 hydrogens get connected to another molecule, each 2 hydrogen bonds. You see, that's very very important thing. Also, you've got 2 lonely electron pairs, and the lonely pairs is where the hydrogen atoms from the other molecule get connected to the oxygen to the other molecule. So this is why we've got very strong hydrogen bonds, not only because of huge electronegativity difference between the hydrogen and the oxygen, but now you've got 2 places where the hydrogen atoms from the one molecule can get connected to the oxygen atom to the other molecule, and this is why we've got such a strong forces which keep the water liquid at room temperature, because of these lonely pairs get connected on the oxygen atom, which get connected to the hydrogen atoms of the other molecule. So now that's another reason so that this can get connected. We're talking about not atomic connection now, we're talking about molecular connection. And this is called hydrogen bonding. So let's revise it one more time. First, we've got London dispersion forces. When the molecules are not polar, when they get together, they start experiencing temporarily dispersion of electrons, and this attraction is called London dispersion forces. One is positive, another one is negative, as you can see. Then the second we've got is dipole bonding, as you can see it here, and a special case of dipole bonding is the hydrogen bonding, which is available only for these three elements: oxygen, nitrogen, and fluorine. As you can see them there on the top of the table, right? They are not so big like a chlorine. Chlorine doesn't make, or a sulfur. Chlorine is just under the fluorine, and sulfur is just under the oxygen. But now they are a little bit bigger, and this is why they can't make this hydrogen bonding, as you can see it here. So let's try to summarize it. All kinds of bondings. All right. Now we're talking about intermolecular forces. We're not talking about between the forces of the atom. And now I've got a question to you. What is stronger? The forces between the atom in the molecule, or the forces between the molecules? What do you think? What's stronger? The forces between the atoms in a molecule, or the forces between the molecules? Now think about the consequences. What would have been if one is the case, and what would have been the case of the other is the case? Of the molecular forces are stronger than the atomic forces. What would have been the case? And what would be the other? Think about it. Obviously, can you imagine that of the molecular forces, the intermolecular forces, are stronger than the atomic force? So that means the first molecule of the same kind that passes through this molecule is going to tear its atoms apart, and there is not going to be anything, only the 120 elements as you know them. So molecules cannot exist if the molecular forces are stronger than the atomic forces. This is why the atomic bonding, it's much stronger than the intermolecular forces. This way, but I just want to say, hydrogen bonding is very, very strong. It's actually 10% of the strength of the atomic bonding, right? It's 10% of the strength of the atomic bonding. The hydrogen bonding, that's the strongest dipole connection, dipole intermolecular force. Now let's start with London dispersion forces. We said London dispersion forces, we've got two molecules of the same kind. When they get closer to each other, then the electrons get dispersed, so they come close to each other. One becomes temporarily positive, one becomes temporarily negative. So now look at it. If you look at the halogens, chlorine, bromine, and iodine. Now chlorine is a gas because the London dispersion forces are not so strong. You see, the molecule doesn't have so much electrons to start get dispersed. But bromine, as you remember from our last lecture, bromine is liquid. The only one of the three elements in the periodic table which is a liquid. The other ones we say is copernicium, and the other one is mercury. Now it's liquid because now you've got more electrons, and now when the molecules are together, the electron clouds get polarized and one get attracted to the other, and this is why this attraction keeps the molecules together, the intermolecular forces, and they start moving around each other, and this is why bromine is liquid. Now let's go to the next element down on this group, iodine. Look, now iodine is a solid at room temperature. Why? Because you've got so much electrons. When they get close to each other, the London dispersion forces are so strong that actually they keep it together. Strong, very, very strong thing. Although this is the weakest of the all intermolecular forces, London dispersion forces. The other one is dipole, induced dipole, which I didn't show you, but I want to show you now. What it means, dipole, induced dipole. You've got two molecules. One is the water, another one is the oxygen. Here, look here. So now what's happening? The oxygen is not polar molecule, water is. So what's happening? The polar molecule, like a little magnet, start pulling electrons from the oxygen, and this pulling creates dipole, induced dipole attraction, and the oxygen gets attracted to the water. This is why our blood carries oxygen. Otherwise, if that wasn't the case, there wouldn't be any fish in the sea, because the fish obviously uses oxygen to breathe, like we use oxygen in our blood to carry through our bodies. Obviously, we've got also hemoglobin, which is very strong attraction of the iron, the hem, with the oxygen. That's another. But also the oxygen is dissolved in water because of this dipole, induced dipole force of the intermolecular forces. This is why we've got the oxygen dissolved in water. Otherwise it wouldn't be dissolved if there wasn't that force. That's another proof that that force actually exists. Then we've got dipole forces. We said it. The water, and also you can see that, say for example, we've got two forces, and let's compare them to similar compounds. One is formaldehyde and the other one is ethane. Now the formaldehyde, this is a very unpleasant smell, has formaldehyde. They use it for a preservation of tissues and dead people in the medicine. So you see it's a polar molecule. We've got oxygen there and we've got hydrogen, almost the same as like a water, just we've got one carbon in the middle. So it's a polar molecule and it's going to get attracted to another polar molecule. So the oxygen is negative and the hydrogens are positive, so they get attracted with the dipole connection. And this is why formaldehyde at room temperature is liquid, and its boiling point is 70 degrees higher than ethane, which is a gas. There is no dipole here. You see, there is no dipole. Look at it. Electronegativity is zero with the whole molecule. There is no difference between the electronegativity. So it is. This is not a polar molecule, and because of that, the only forces that can experience London dispersion forces, and that's not enough to keep it liquid at room temperature. You see it now. Now the next one is the strongest of the dipole forces, and that is hydrogen bonding. The hydrogen bonding is responsible for liquid water, and also it's very responsible for the structure of ice. Now look what's happening, is getting 6 oxygen atoms and 12 hydrogen atoms, but they are turned to each other because of this hydrogen bonding. The hydrogen gets connected to the oxygen, and we've got a hexagonal structure with 6 angles. This is why, because of this hydrogen bonding, the water freezes and the ice floats actually, because of this hexagonal structure Otherwise, the water we saw has a tetrahedral structure. We saw it. Now this is hexagonal structure, which is much bigger. We're going to study that. Don't worry, I'm just saying you now why we've got hydrogen bonding and how this hydrogen bonding contributes to the ice floating on water and not water floating on ice. All other substances, almost all of them, when it's solid, it sinks down. When it's liquid, it's up. Water, take a benzene. Benzene, when it's solid, it sinks down. All right. But the water, when it's solid, it floats because, you see what's happening? Hydrogen bonding actually opens the molecule from the tetrahedral, like a pyramid, makes it hexagonal, like this. So it's bigger, you see. This is bigger than this. Do you see it? So now you've got hydrogen bonding responsible that water expands when it freezes. This is why the ice floats, because it expands. And the strongest force is the ion dipole force between the one ion and dipole. Dipole is, say for example, the water is dipole, and ion is when you dissolve salt in water. When you dissolve salt in water, what is happening is the salt, because it's ionic compound, there is no covalent bonding, they don't share electrons, one has stolen the other one, it's disintegrated into ions. Look what's happening. The water surrounds sodium ion and the negative ion, which gets also attracted to the positive part of the molecule, to the hydrogen part of the molecule. While sodium, because it's a positive, gets attracted to the negative part of the molecule. This is why dipole ion connection is responsible of, this is why we've got ions dissolving in water, like sodium chloride. Otherwise, sodium chloride wouldn't dissolve in water. For example, calcium carbonate or marble doesn't get dissolved, or a stone doesn't get dissolved in water. Silicium oxide or a glass or a sand also doesn't get dissolved in water. You see, because there is no disintegration in ions. But now when you've got ions, what's happening? The water molecule is turning his negative charge to the positive charge of the ion, and his positive charge of the water turns to the negative ion. And this is why we've got ion dipole connection, which is the strongest connection of the intermolecular forces. So now I hope you understand now why the water is solid when the temperature is under zero, because of this hexagonal structure, and why the water is liquid at the temperature above zero at sea level pressure, 1 bar pressure. So now what is happening is, this is why we've got all of these beautiful waves at temperature above zero, and this is why I've got liquid water at room temperature, because the molecules have strong hydrogen bond. Now let's compare this molecule, water molecule. We said we've got steric number of 4, and it's a tetrahedral structure. We've got 2 lone pair electron clouds and 2 bonded electron pairs. So I've got 4, it's like a pyramid. Now we're going to take a similar molecule with exactly the same steric number, 4. That's hydrogen sulfide, the smell of a rotten eggs, right? And this is gas. The water at room temperature is liquid. Why? Same steric number, same bent molecule, all right? But now look at it. First thing, the molecule is not polar. Electronegativity number of sulfur is 2.5. Electronegative number of hydrogen is 2.1. So the electronegativity is 0.4. And I said to you, when it's 0.4, it's not polar. While the water molecule is polar. Now we've got two lone electron pairs clouds, just like the water, and the structure is also tetrahedral. They are also bent, they are actually bent more than the 105 degrees between these two atoms in this bond. So we've got similar bending, but now because of the hydrogen bond is missing in the hydrogen sulfide, there is no hydrogen bonding, because the bond between the hydrogen and sulfur, there is not so much electronegativity like we've got here. You see, hydrogen and oxygen, they've got difference of 1.4, and there is the difference only 0.4. That first, and also sulfur is not one of the three elements that make hydrogen bonding. There are nitrogen, oxygen, and fluorine. As I said to you, sulfur, which is the next element under the oxygen, doesn't make hydrogen bonding, because the difference of the electronegativity between the sulfur and the hydrogen is not so big. This is why we don't have hydrogen bonding, and this is why hydrogen sulfide is a gas and the water is liquid. So that's very important to understand it. And this is why hydrogen sulfur, although you can see the steric number and the valence shell electron pair repulsion theory shows us that the structure is tetrahedral, same like a water. The one is gas, another one, simply because of hydrogen bonding. You see, that is very important to realize. Now, because of that, because of this hydrogen bonding, ice is solid under 0 degree. You start making these hexagonal structures, which I showed you, and I'm going to show much in detail in the next lecture. When these hydrogen bonds start getting loose because of the temperature, now the electrons of the energy of the atoms get higher, and now you've got another force, the moving force, the kinetic force of the atoms. It gets stronger now than the hydrogen bonding force. The molecules start moving around each other. They start rolling each other, not like with the ice, hexagonal, fixed, sturdy, robust structure. Yeah, the hydrogen bonding start getting disintegrated so much because we've got kinetic energy. We've got two competitive forces. One is kinetic energy because of the heat, and the other one is the strength of the hydrogen bonding. These two are competing, and now one is start overwhelming the other one, and this is why we've got hydrogen bonding, but it's just created for a second, and then after another it's losing. It's not so sturdy. And now when the hydrogen bonding is completely overwhelmed and overcome by the kinetic energy, we've got gas, we've got water vapor. You see how how beautifully explained the theory of bonding, hydrogen bonding, and what we studied in this lecture explain why the water is solid, why the water is liquid, and why the water is gas. See, when it's gas, the molecules are very apart of each other. They are not bonded. They're just flying around. Their kinetic energy is very high, not like with the liquid, and not like so that they can move. So let me show you this with another presentation. Look at it. This is minus 120 degrees Celsius. That means the water should be solid. Alright. When it's solid, we said that the molecules get in a hexagonal shape, and they just shaking little bit, but they don't roll over each other. When you start heating and we move the temperature above zero, the molecules start rolling over each other because some of the hydrogen bonds get destroyed. There is still some hydrogen bonding, but they're created and they destroyed it continuously because, as you can see, the molecules are rolling over each other. And the more heat I put, you've got the more kinetic energy. Now, when I put kinetic energy more, when I put heat more, I increase the kinetic energy. Now I can see they start moving faster and faster and faster. And when it's 105 degrees, you can see some of the molecules start flying. The water is boiling actually, and the water becomes gas, completely evaporated. Now you can see the molecules, there is no hydrogen bonding between them. There is no hydrogen bonding, there is nothing. See, there is nothing. There's no sturdy structure, there is no rolling over each other, just flying around. See. And this is actually the three phases of water, and this is why they exist, because of this hydrogen bonding. So let's summarize what we studied today very quickly. We studied how the atoms get connected and how the molecules are bonded to each other. And we said that the intramolecular forces, that means the forces between the atoms in the molecule, are much stronger than the forces between the molecules. Otherwise, the matter will disintegrate. Of the one was there. Remember, there was 4 atomic bonding forces, and that was ionic bonding between ions, like a sodium chloride. One is negative, another one is positive. Then you've got covalent bonding between equal electronegativity atoms. That means like the oxygen and oxygen gets O2. There is no polarity. And then we've got polar covalent bonding, like the water, where one part of the molecule has positive charge, the other one has negative charge, because the electronegative oxygen pulls electrons to each other. And then we've got metallic bonding, these 4. And we said that we can discern the kind of bonding if it's under 0.4, it's covalent. If it's above 0.4 up to 2 is polar covalent, and if it's above 2 it's ionic, like so. And we also said about the metallic bonding and why mercury is liquid and why gold is golden color, yellow. Now we studied also intermolecular forces, the forces between the molecules. And we said about intermolecular forces that the weakest of them is London dispersion forces. When 2 molecules are covalent molecules, non-polar molecules, get near to each other, the London dispersion forces disperses the electrons to one and makes it temporarily one positive, another one negative, so they get attracted. And this is why with London dispersion forces we've got liquid bromine and solid iodine, but you don't have liquid chlorine. Chlorine because you've got few electrons, not so big as the iodine. Chlorine is a gas, iodine is a solid. Then we've got dipole, induced dipole, water and oxygen. When you've got dipole, that's water molecule, and then you've got non-polar molecule like the oxygen or a nitrogen. And this is why they get dissolved in water, because temporarily one is inducing, this dipole is inducing the other molecule to pull with positive to the negative charge. Actually, if you take magnet and if you take iron, which is not magnetized, still is gonna do it exactly by the same way. It's going to induce the electrons to move to this way. The positive to negative, they're going to get together. The other one is dipole. That's like a two magnets. The positive charge goes to the negative charge, and the two magnets get together. Red and the blue get together. The southern and the northern pole of the magnets. This is why we say formaldehyde is a liquid while ethane is gas. That's a dipole. And the strongest of the dipole connections, we said it's a hydrogen bonding between nitrogen and hydrogen, oxygen and hydrogen, and fluorine and hydrogen. And this way, these three elements, because they is small, the hydrogen bond is very, very strong. While the fluorine, and we said hydrogen sulfide is a gas. This is why water is a liquid, simply because of that. The electronegativity between electronegativity of sulfur, and the difference between the electronegativity between sulfur and hydrogen is not so big as the electronegativity of nitrogen and the fluorine and the oxygen. So this is why we've got hydrogen bonding, and this is why we said the ice gets hexagonal structure, while the water, when it's liquid, has a tetrahedral structure like a pyramid. And the strongest bond ever existing between molecules, if you can call it ion, it's not a molecule technically, but that's the strongest bond between the molecule and a particle. That's ion dipole. When salt, this is why salt is dissolved in water, because when the salt gets into the water, is dissociating between the molecule. It's actually not a molecule, it's a unit of chlorine and sodium ions in the lattice. They get dissociated in water, and the water surrounds the oxygen, is surrounding the sodium. Sodium is a positive, oxygen is a negative, as you know, and also hydrogen is surrounding the chlorine, because hydrogen is a positive and the chlorine is a negative. They actually break this lattice, because this energy, ion dipole bond, the energy of this bond is stronger than the lattice energy. This is why the lattice get disintegrated, and this is why you don't see any more crystals of salt when you put it in the water. It gets dissolved, and this is why the water gets dissolved. I hope I explained it clearly. If something is not clear, go back and study it, and next time we're going to study the kinetic and the thermal properties of water, and we're going to see how they also make water what it is. I hope I'm going to see you next time. Until then, study.